So here it is. If a diffraction grating produces third order bright spot for red light is 700 nanometers at 65 degrees from the central maximum. So here is a diffraction grating here. Here is the center. And then for red light, for everybody, this is 0. For red light, let's say here's 1, 2, and then 3. So this is 3. And they tell me that the angle is 65 degrees. Theta red is equal to 65 degrees. Okay? And we know, we're told lambda red is 700 nanometers. It says here, at what angle will the second order bright spot be for violet light? So here is violet. You have the color. So let me ask this one. Here is m equal to 1 for red, m equal to 2 for red, m equal to 3. Will the violet first one be below or above this one?
Below.
Below because shorter wavelength, right? Yeah, you got theta, you got m lambda over d, so lambda is smaller. Yeah. So for violet, you'll have, here's your first violet, and then maybe your second one might be here. So they want to know the second order, what angle does it make? So here's the second order. So here's 1, here's 2. They want to know this. Theta v is equal to how much? Right? What would the steps be to solve this? What would be the steps to do this? And oh, I need to give you the wavelength for violet. I think it's 400. What would you do to solve this? You can do it. What are the steps?
We get the distance by using the angle we're given and the
Yeah.
wavelength of that.
So use the red information to find D, and then use D to find the angle for violet, right? Yeah, because D is going to remain constant, right? D is the same. Yeah. And so since D is going to be the same, yeah, I let you do it for a moment. Okay. So here's how I would do this. We know d sine theta is equal to m lambda, so d will equal to m lambda over sine of theta, right? That's d. So d will equal to, if I use red, what's m for red?
3.
Yeah, it is 3 times lambda red, which is 700 nanometers, divided by the angle for red, which is 65, right? But that same D is equal to 2 times 400 nanometers divided by the sine of the angle for violet, right? Yeah. That way, I will, if you don't want to, really don't want to calculate D, you don't have to. So we got this. So cancel these, okay, from both sides. And then cross multiply and divide. So cross multiply, 3 times 7 is 21. So we got theta violet will be 2 65 degrees divided by 21, sine inverse of all that. Okay. The thing. Okay. So, and that should give you 20.19 or 20.2. 20.2 degrees. And one more topic, which is about resolution. We've been talking about slits, right? And how about, let me show you. What if we have like a circular opening, a circular hole, and you let light go through it? Did I make a mistake?
I think it's 8 sine 65.
8? Where did you get the 4 from? Oh yeah, I forgot about this 4, yeah. So 8 here? Okay. How about now? Does it look good?
Yeah.
Yeah, thank you. It seemed like something was missing. Okay. And I'm going to erase this board here. So, if you have a screen here, if you have a single slit, here's a screen. Imagine the single slit is here, somewhere here, and you send light. We said we see the following. We see a bright spot, right, in the middle, and then we see dark, and then we see bright, and then we see, and then bright, and then we see dark, and then there will be bright, and so on, right? So let me just draw bright, bright, and then dark. So this is for single slit. And this, again, here is the slit, the opening is here. Okay? The opening is here, and the light is going through. What if, I drew it this way so that I can't draw in 3 dimensions, so I'm purposely doing this. So for let's say now I have a circle, instead of just a slit that looks like this, we have a circle, a circular hole, and then the light will go through that hole, and then what do you think you would see?
Rings.
It would be circles, yeah. It would be this, it's like you take a slit and you rotate it by 180, right? So what does it draw? So what you would see is in the middle, there will be a disc, and it would be bright. So there'll be a bright disc, big bright spot, circle. Around it, what used to be a dot becomes a circle, a dark circle. And a dark circle. Okay? It's a dark circle, like this. And then you will have another bright circle around that, like this. And then what would be around that bright circle? A dark circle, right? Like this. And so on, okay? And then bright. That's what would happen. Okay? For these, when we have these, this is 1, 2, -1, -2, for these, what we said, the angles were like this. The angle theta, for example, theta 1 was lambda over a, right? Lambda over a. No, sine theta 1, sine of theta 1. Sine theta 1 was lambda over a. Okay. And then sine theta 2 was what? Is twice lambda over a, right? Yes, I'm quoting this. A sine theta is equal to m times lambda. That's the one I'm trying to quote. For here, we talked about the slit size. For when you have a hole, we'll talk about the diameter of that circle, diameter of that hole. So the diameter of the hole that's here, it will be like, imagine the hole is here, it will have, and then the light goes through it, then it will have a diameter d for diameter for that hole. Okay. Diameter is d. Now, what are the angles in this case? What angles? What are the angles? The angles go as follows. Here's the center, and I need I know the first one, and then that's the one we need to know. The rest is just a curiosity. So the first dark ring will happen at this angle. These are the thetas. So sine of theta 1 is equal to, you might guess it should be, what should it be? It will be lambda over what? Here, the size of the slit is A, the size of the hole, the diameter of the hole is D. Lambda over D. And what, should this be 1? It turns out not exactly 1, just from geometry. More careful analysis turns out to be 1.22 lambda. So this is an approximation. The numbers go on. So it's 1.22 lambda. How about to the second one for theta 2? Turns out to be, you can find these numbers. I'll just write this one and then stop. It's 2.23. Okay? And then I will stop. That's it. That's good enough.
Where are you getting the 1.22 from?
It's more careful geometric analysis, which we're not going to go into. It's in more specialized books.
In the equation though, what is it taking into account? Is it
The
part
geometry of a circle.
of A? So it would be a part of A, the A replacement.
Yeah. It wasn't just a simple rotation by 180 and then you just say A becomes D. There is this extra geometric factor that comes up. Okay, it's 1.2. And then there are other angles listed. The next one is like, it would be 3 something, and so on, okay? 3.24, yeah. How do you know? It's in the book.
It's it increases the.
I see. Oh, okay, got it. Okay, yeah. And then there is an equation for the bright ones also. We only need the first. We just need the 1.22. That's the one we need, right? We just need the 1.22. Okay. So this brings us to resolution or Rayleigh's criterion. Okay. So let me ask you this. Let's say, have you seen when you're driving at night, you see a car coming from very far away, but when it's really, really far, right? The car has 2 headlights. Okay. A car would have 2 headlights, right? Usually. And then, if both are working. But if it's too far, sometimes you think they're just one headlight when they're very far away, right? You think it's just one light. And then when you think it's like a motorcycle or something. So, but when it gets closer, you finally can resolve it and think, oh, it's actually, the light I was seeing is coming from 2 sources, not just one, okay? And that's called resolution. So if something's too far, you can't resolve it. So let me draw it here. So let's say, obviously this picture is greatly exaggerated. Here is the person's eyeball. That's eyeball for the person, yes. And then the car is here. See, the car becomes point. And the car is way too far. It's very far, right? You're talking about a mile or many yards away. So this one, it will go through the slit. What's the slit? That's the, or what's the hole? Why do we care for the circles more? We all have a pupil, and the light will go through that pupil. Okay. So this one, going here is our pupil. So it will go through it, and then we will see a diffraction pattern in our, this is our retina here. So you will see a bright spot in the middle, and then these are the dark ones, okay? And then for this one also, we'll see a dark spot, and then, so they're far away, we can resolve them, right? I mean, they're close enough, the cars here, or the two lights, we can resolve them. But if they get too close, yeah, if they get, let's say now, let's draw, maybe they're here now. They get a little closer to each other. Let's draw them a little closer like this. A little closer. Then maybe this one will have this, and then the other one, they will overlap a little bit. Okay? When do we not resolve them? We can't resolve them when this happens. Let me draw the eye again. Here's the pupil. And let's now use red. Let's say they're here now. One is here and one is here. Let's say this is the maximum of this one, and the maximum of that one is here. I messed up with this line. So here. The dark spot of this one coincides with the maximum of the other one. Okay. Then you can't resolve it. Okay. You can barely resolve it, or maybe not. Okay. Does that make sense? So if you're talking about, if we're looking at these two discs, here is the first disc, and here, let's represent it as a disc. So here's the first disc, that's the center. If the other one's disc, the dark spot of the second disc coincides with the center of the bright disc, of this other disc here. So these are the two centers. Then you'll not be able to resolve it. Okay. And if they're farther than that, obviously even worse, right? So you can't resolve it. If they get closer, then you start to tell, you're able to tell that you have two different sources. And that criteria is called Rayleigh's criteria. So I will just state it in words, I will read it. It says, if the first dark fringe of one circular diffraction pattern passes through the center of a second diffraction pattern, then the sources responsible for the pattern will appear to be a single source. So when they're like this, you can distinguish them. But when, so this is the dark, right? Surrounding the bright. So when they overlap like this, you can still distinguish them. But then when this dark overlaps with the middle of this one, then you cannot distinguish them. Okay. So when does that happen? Well, at what angle? Well, we know the angle this way, from the center here to the first dark, is given by 1.22 lambda over d, right? So you have here from the center to the dark, this is theta. If theta, or sine theta, is 1.22 lambda over d, then you cannot distinguish it if it's less or equal to this. Okay. If this is theta, then this is also theta. Let's do an example, and then hopefully it'll get clear. So that's the minimum angle, right? That's the minimum angle. So let me write again. Sine of theta minimum, this is the smallest angle that you can resolve, is 1.22 lambda over d. And usually this angle is very small, so it's basically equal to theta. Okay, theta minimum. So let me write, if it's small, this is small, then we get theta minimum is equal to 1.22 lambda over d. Theta, notice, will be in what units? It's not going to be in degrees, right? It's going to be in radians. The angle, when it's a small, the sine is equal to the angle in radians, right? For example, 2 degrees is a small angle, right? But sine of 2 degrees is not equal to 2. Sine cannot be 2. Okay. I'm surprised at how much time flies by. I thought I'll be done in like 45 minutes, but I wasn't. So let's do this example here. It says, find theta minimum for green light and an aperture diameter of 5.77 millimeters. So here's the first example. Let's say lambda is 535 nanometers, and the diameter is 5.77 millimeters. Then we get for theta minimum, we'll do a more relevant example. This one is just computational. Theta minimum will be this, right, 1.22, and then lambda, which is 5.35 times 10 to the minus 7 over 5.77 times 10 to the minus 3, and we get really small, 0.00013, 113 radians. Okay, so the angle is small. Notice resolution, theta minimum is even smaller, right? If you can, the smaller theta minimum is, it means you have a better resolution, right? You have more resolution power. So for example, if somebody's at night, or like an eagle or something, they have a larger pupil diameter than a human. I think it's almost like twice. So they can resolve things from far away even better at twice the angle we have. So they can be like twice the distance, right? So here is this example. Let's say here is a car. This is the next example. Here's a car, right? Coming towards you. Here are the headlights for the car. And the headlights for the car are separated by a distance y equal to, let's say, 1.5, that's just 1.1 meters, okay? I was going to use different numbers, but that's okay. That's y, and then your eye is here. Here's the person's eye, and then light comes in, right? And the question is, if your pupil, so if d is equal to, what do you think the human pupil is? Obviously it depends whether it's dark or bright, right? It gets dilated.
2 to 4 millimeters, 4 to 8 if they're adults, so I'm just guessing.
Good guess. Let's say 5 millimeters. Yeah, good guess. 5 millimeters. And let's say the car's headlight is not going to emit, it's not laser light, it's going to emit a band of wavelengths. But let's say on average 400 to 700, so halfway you're talking what, like 500 nanometers, right? So let's assume lambda is 500 nanometers. Okay. The question is, how far can the car be this distance, this way, L? How far can the car be and you still can resolve, you can see the two headlights as two? Right? How far can the car be and you can still see the two headlights distinct? If it gets farther than that, then you cannot see it. Okay? Is the question clear? What should L be? How far can the car be? The maximum L, right? Maximum L corresponds to the minimum theta. So we know theta minimum is equal to 1.22 lambda divided by d, right? But also, I know here's theta minimum. It's a small angle, so I know that if it's a small angle, I know that L times theta is equal to y, right? The arc length. Not quite an arc length, but approximately. So L theta is y, so theta is equal to y over L. Theta is equal to y divided by L. So I'm going to equate this to also y divided by L. So we're going to cross multiply and solve for L. So we get L is equal to d times y divided by 1.22 lambda. Okay? That's what I was going to try to do. I was going to say let y be 1.22 meters so that it cancels. But that's okay, we have calculators, so we can plug it in. Diameter, 5 millimeters, so 5 times 10 to the minus 3. Y, 1.1 meters, 1.22, and then lambda, we're talking 500, so 5 times 10 to the minus 7. And if you can tell me what you get, that'd be great. 9,000? About 9,000 meters, right? Meters, I'll put approximately. So 9 kilometers, about 6 miles. Technically, we can resolve even more than this. I ignored something. Can you think about what I ignored? Dilation, okay. That can be a factor. Lambda. This lambda here, it's inside the eye, so it will be divided by the index of refraction of the eye, which is like 1.33. But that's okay, that's a decaf. So 9 kilometers. This puts an end to this chapter, and I'm going to, let's see here. Yeah, it says in here, of course this is, I mean, do you think you can see a car from 6 miles away? 9 kilometers? Yeah, I mean, this is like ideal, in a real situation, there is like, there are some other blurring effects from the atmosphere and so on, so you're probably going to be reduced a lot more. Okay. So on Monday we're going to start a new chapter. It's going to be chapter on relativity. I might do a couple more examples. I will see over the weekend if something comes up. Okay. Let me pause this here.